Okay, we're back. Here is the third video on the third section, which was section 4.4, all about concavity and points of inflection. Let's just begin. The very first problem, number 8. Directions are determine the open intervals in which the graph is concave up or concave down. And we are given just a polynomial. So here it is, h of x equals x to the fifth minus 5x plus 2. And so what happened in this video is we defined this concept of concave up and concave down based on the existence of the tangent lines, and then we proved that it's the second derivative of the function which is telling you about concavity. And so the thing to do is to take the derivative. What is the derivative? Okay, 5x to the fourth minus 5. And what is the second derivative? Well, it's just going to be 20x cubed. And okay, that's pretty simple. And so we now make a sign chart for the second derivative, and we see that, well, if you cube a positive number, it's positive, and if you cube a negative number, it's negative. And so the second derivative sign chart looks like this. Since h double prime is positive on the interval 0 to infinity, we conclude that f is concave up on the interval from 0 to infinity. But since h double prime is negative on the interval negative infinity to 0, we conclude that f is concave down on the interval from negative infinity to 0. So that's it. Okay, I'll just move on. 9. Is this just the same problem, just more maybe work to do because it's a harder function or something? But actually not even. Here is the function. The function is f of x equals 2x minus tan x on the interval from negative, specifically on the interval from negative pi over 2 to pi over 2. Well, we take the derivative. What do we get? Ugh, I don't feel like doing this. Well, we're going to get 2 minus derivative of tan is secant squared. And then we take the derivative again. Okay, that's 0. So now what's the derivative of secant squared? Where it's going to be negative 2. Derivative of something squared is, well, it's just going to be secant x back inside for the derivative of secant, which is secant x tan x. And, alright, maybe this is a little bit silly. What we end up with is negative 2 secant squared x tan x. And now I have to make a sign chart for that. Well, that doesn't sound fun. But I just know things about tan, right? I mean, I just know that on the interval from negative pi over 2 to pi over 2, tan is going to look like that, of course. And secant squared will always be positive, and tan will be negative until 0 and positive thereafter. So if we're looking on the interval from negative pi over 2 to pi over 2, then on this interval tan will be negative, but there's also a negative here which makes this positive, and then this is negative. So this is the sign. This is me just knowing so much pre-calculus that I can easily produce a sign analysis on this second derivative function. It's a little bit cramped in here, so let me just show clearly what I'm doing. I took the derivative twice, I got a formula for the second derivative, and then I made this sign chart to figure out when this second derivative is positive and when it's negative. And the answer is it's positive here and negative here. And so we conclude that this function is concave up on this interval and concave down on this interval. And I think that's just right, yeah? If you look at the graph of the tan function, you'll see that the tangent lines will be above the curve until we get to 0, and then after the tangent lines will be below the curve, which is the definition of concave down. Good. 2 down, some to go. 15 is just more of the same.
find the points of inflection and discuss the concavity, which is just another way of saying figure out whether the function is concave up or concave down. Okay, maybe this homework is kind of short. I don't know, we'll see. So here we go. F of x equals x times x minus 4 to cube. Okay, and directions, find the points. Okay, so we go. We begin. I guess I'll just use the product rule. Not sure if it's a good idea or not. Sure. Okay, so I don't feel like multiplying this out, so I'll just use the product rule. So derivative of the first times the second, so that's x minus 4 cubed. Derivative of the first times second plus the first times the derivative of the second, and the derivative of this is 3 x minus 4 squared, back inside for the derivative of x minus 4, which is 1. Okay, and here it's very tempting to simplify this a little bit. Maybe that's a good idea. I don't know. Sure, let's do it. Well, might be a waste of time. I don't know. Okay, if I simplify this, then I can take out an x minus 4 squared, and I'm left with x minus 4 plus 3x. If I did that right, and I did, so that's 4x minus 4. Okay, so that means that the first derivative is x minus 4 squared times 4x minus 4. Okay, I guess I'll just leave it like that. Just double check all this work really fast. The first times the same plus the first time the derivative looks like, yeah, looks good. Yeah, okay. Well, I need the second derivative, so we push on. And again, I'll use the product rule. So derivative of the first, which is 2x minus 4 to the 1, back inside of the derivative of x minus 4, which is just 1. So the first times the second, plus the first, so x minus 4 squared, times the derivative of the second, which is just 4. I don't know if this was the most efficient way to do this, but anyway, I have taken the derivative twice, and now I have this big old polynomial. What can I do with it? I guess I can take out a 2x minus 4, and that leaves me with, or I can, man, this is kind of annoying. Well, whatever. I'm going to take out a 4, x minus 4, in fact, and that leaves me with, so I took out a 2, I took out an x minus 4, but I also took out a 2 out of this. So that leaves me with 2x minus 2, if you're following this. Plus, I took out a 4 and one of those. Okay, doing just like a whole bunch of algebra that's a little stupid, and maybe I'm going too fast and maybe too slow, but I think this is 3x minus 6, and which really means I could have taken out a whole nother, well, okay, and then I'm going to get another 2, so it's 8x minus 4, x minus 2. I'm fairly confident that I did all that correctly, but it's just algebra, mostly, because that's just 4 times x minus 4 times a 2. Yeah, it's just all right. I'm just right. 3x minus 6. Yeah. Okay. And so what did we learn? We learned that this function has 2 numbers for which the second derivative is 0. And let's now make a sign chart for the second derivative. And the second derivative is going to change sign at 2 and 4. And it's a quadratic, so it's going to be like this. So it's going to be plus minus plus. And so what we now know about this function is that it will be concave up here, concave down here, and concave up here. And perhaps it's worth it to make a quick sketch of this function. What do you know about x minus 4 cubed? Well, this is another function that in pre-calculus we could have graphed decently well. I know that it will, if you give me something bigger than 4 here, it will, well, I'm going to change sign at 0 and 4. So it's going to be plus minus plus. Now I'm back to talking about the function. And of course there's a root at 4 and a root at 0, and there's going to be like a triple root here. And so what does this function look like? Actually, it looks like this. F of 0 is 0. F of 4 is also 0. There, it's going to be positive it's going to be positive to the left of 0, negative in between here, and there's going to be a triple root at 4. So, sorry, kind of zoning out for a second. So, okay, so it's going to look something like this. There's going to be a, well, here's what I could have known already in pre-calc. What I could have known already in pre-calc is this is going to be positive, then negative, then a triple root at 4, and then positive again. So this is what a good pre-calculus student should have drawn. But this is a little bit wrong. And what I now can tell you is that something very exciting is going on at 2. And if I plug in 2, okay, it turns out that this is quite big. If I plug in 2, I get negative 16. So way down here at negative 16, something happens. And the thing that happens is, and I think there's a minimum here at 1 as well. So this is terrible. And if I had a bigger board, I could do this justice. But basically, what we have here is at this point 2 comma negative 16, we have a point of inflection. And the graph just straight up tells us that the function will be concave up until we get to 2. And I've drawn this relatively well. What does it mean to be concave up? It means that the slopes of the tangent lines will lie below the curve, and that certainly seems to be the case, right? That all these tangent lines lie below the curve. But then at x equals 2, something changes, and now the tangent lines lie above the curve. And then after 4, we get a change again, and the tangent lines lie below the curve. So this function is concave up, hands up in the air, concave up. Tangent lines lie below the curve, hands in the air, under the elephant. So this function is concave up, then concave down in between 2 and negative, in between 2 and 4, and then concave up after that. I hope this picture's clear. Okay, good. That was sort of a demonstration of how this notion of concavity enables us to graph this function pretty well. And yeah, there you go. And okay, I'll just say, since I made this picture already, that what's really going on here, the best way to talk about this point of inflection, so this is a point of inflection, but this is also a point of inflection, is that they are there. So here we have this function which is getting smaller, so let's just say getting worse. It's getting worse. And here, just by kind of eyeballing this derivative, I see that it's going to change sign at x equals 1. So there must be a relative min here at x equals 1. And then the function starts getting better. And it starts getting better at a faster and faster rate. And what's happening at this point of inflection, x equals 2? At x equals 2, the function, the rate at which the function is getting bigger starts getting smaller. So we have a function which is getting bigger at an ever-increasing rate, and then starting at 2, it's now going to get bigger at a slower rate. And then, at x equals 4, it starts getting bigger at a faster rate again. So that's kind of all. So it's the moment at which the derivative changes from positive, the derivative goes from increasing to decreasing. Here the derivative is increasing, then the derivative is decreasing, slowing down, then increasing again. Okay, hopefully that made sense. Let's just do the rest of these problems. I think they're all kind of the same, or the directions are the same, mostly, or many of them. Okay, what's 17? Yeah, just another one of these, man. Here we go. Here is, and I swear this is like important,
find the points of inflection and discuss the concavity. So the function is x root x plus 3. Oh man, let's go. So, once again, we'll write this function as x times x plus 3 to the 1/2, and now we are going to take the derivative. And we need to use the product rule together with the chain rule. So, derivative of the first times the second plus the first x times the derivative of the second, and the derivative of x plus 3 to the 1/2 is 1/2 x plus 3 to the negative 1/2 back inside for the derivative of x plus 3, which is just 1. So that's not too bad. Alright. Maybe we should simplify, or maybe we just push on. Let's just push on. So this time I won't do intermediate simplification. I'll just take the derivative again. So what's the second derivative? Well, the second derivative is going to be, well, I need to take the derivative of x plus 3 to the 1/2, so it's going to be 1/2 x plus 3 to the negative 1/2 plus, and now let me be careful, I'm going to do the product rule again. So this is going to be the derivative of the first, which the derivative of 1/2 x is just 1/2, times the second, so x plus 3 to the negative 1/2, plus the derivative of the first times second plus the first, so 1/2 x, times the derivative of the second. So the derivative of the first times the second plus the first times the derivative of this. So what is the derivative of x plus 3 to the negative 1/2? It's negative 1/2 x plus 3 to the negative 3/2. Okay. So now I have this big bunch of stuff. Can we simplify this? I feel like we can. So these two just add up to be x plus 3 to the negative 1/2. And over here, we have negative x over 4 x plus 3 to the negative 3/2. And this is just hard. So we should try our best to simplify this. And the way to simplify it is to factor out x plus 3 to the negative 3/2, because that's the lowest power. And I'm also going to take out a 4 because I want fractions out of my life. Well, if I do that, then I'm left with 4 times x plus 3 to the 1, because something to the negative 3/2 times something to the 1 will be something to the negative 1/2, and this 4 is to cancel the 1/4. And then over here, I guess this is just minus x. Yep. And so what's here in the bracket? It's like 4x plus 12 minus x. In other words, 3x plus 12. In other words, oh man, what happens when all of this gets simplified? We end up with, on the top, 3x plus 4, and on the bottom, 4x plus 3 to the 3/2. And that is the second derivative. Okay. What was the point of all of this? Well, perhaps we should make a sort of note about this problem, which is that I actually cannot plug in anything less than negative 3 into this function. So the domain of this function is only things from negative 3 to infinity. If you plug in anything less than negative 3, it will be undefined. And so, after all this work, I actually find that this is a little bit of a silly problem, because I'm now forced to make a sign chart for this. And what does the sign chart for this second derivative look like? Well, there's a sign change if I'm just looking at this second derivative and not thinking too much, I notice that the denominator is always positive, and so I only need to care about the numerator, and the numerator changes sign at negative 4, and from negative to positive, which is another way of saying, that's the right answer. But now, thinking a little bit more about this actual function, we see that its domain is only from negative 3 to infinity.
And so the sort of correct sign chart for this is just starting at -3, and the answer is that this second derivative is always positive. So it took a lot of work to determine that this function has a positive second derivative for all numbers greater than -3. And that's actually not so surprising if you go to make a graph of this function. What is the graph of this function going to look like? Of course, if you plug in -3, you're going to get 0. If you plug in 0, you're going to get 0. If you plug in a number between -3 and 0, this will be positive, but this will be negative, so the product will be negative. And beyond that, if x is positive, then these will both be positive. And so what you get is just something that looks a lot like this. This is pretty much what this function looks like. It's going to be sort of locally quadratic or locally square root-ish, I should say, at -3, and locally linear at 0, and it's going to look kind of like this. So, it's actually very clear that this function should be concave up always, because, and I'll just use this opportunity to keep doing it, the tangent lines to this graph are always lie below the graph. Or, what's an equivalent way of putting it, the derivative is always increasing. That's another way of giving a definition of concave up. In my class, we define concave up as tangent lines lie below the curve. But an alternative definition of concave up, this is the one in our textbook, is that the derivative is always increasing. And here we see the derivative starts as a big negative, then it becomes a small negative, then it becomes like a 0, then it becomes a small positive, then it becomes a bigger positive. And so these three things are all the same. That the derivative is increasing is obviously the same thing as saying f double prime is positive, because it's simply the theorem from the previous section applied to the derivative. So we know that when something's derivative is positive, it's increasing. So here, if the second derivative is positive, then it means the derivative of the derivative is positive, so that means the derivative must be increasing. So I think that should be pretty clear. And then the one that's not so obvious is but true is that, okay, run out of space, but I guess I'll just do it like this. F is concave up. We proved in class, well, you watched on the video, and it's a kind of a hard proof, that if f is concave up, or rather we proved that if the second derivative is positive, which means that f prime is increasing, then it means that f is concave up, where for us, concave up means tangent lines lie below the curve. Okay. Good. Chop. 3 more problems. Just erase all this. All right. Okay. 21. Yeah. 21 is just more of the same. Oh, did I actually? Well, okay. 21. I think I finished that problem. So f of x equals sine x over 2. Okay, this is, well, and we're going to do it on the interval from 0 to 4 pi, and I think the directions are still just the same, right? Find out where it's concave up and concave down, and find the points of inflection. Well, we begin. What is the derivative of this function? The derivative of sine of x over 2 is just cosine x over 2. Back inside the derivative of x over 2, which is 1/2. And what's the second derivative? Well, it's now just 1/2 times, what's the derivative of cosine x over 2? It's negative sine x over 2. Back inside for the derivative of x over 2, which is another half. And so when we're all done with this, we just get negative 1/4 sine x over 2 is the second derivative. And now this boils down to determining when is this positive and negative. Okay, so I need to know when is negative 1/4 sine x over 2 going to be positive. Okay, Well, clearly that's just whenever sine x over 2 is negative. And when is sine x over 2 negative? Oh, okay. This is actually a little bit hard. Let's see. How did we do this back in pre-calc C? We said this involves some care, I guess. Well, what's the smart way to do this? Okay, the smart way to do this is to say, let's make a picture for x over 2. And here's the x over 2 picture. The x over 2 picture is, when is sine of x over 2 negative? Well, the sine of anything will be negative when the y coordinate is negative. And so we're talking about this. Okay. And so that's the picture associated with this equation, where we're sort of, it's almost as if we're temporarily calling x over 2 like theta or something, and then we're doing it like we normally do. Okay, and now looking at this picture, it's tempting to say, okay, well it's just everything between pi and 2 pi. So if x over 2 is between pi and 2 pi, then that will be then the sign of it will be negative. That's true, but there's more to it than that. It's also, you could also go around the whole circle again. And so it's also a more general thing to say is that if x over 2 is anything like pi plus 2k pi and 2 pi plus 2k pi. Is this what I want to do? Yeah, because if I go all the way around the circle again, well, you know what? This is just actually it doesn't matter for this particular problem because you can just it's kind of stupid a little bit. Okay, I haven't really thought through this, but if you just multiply this by 2, you just get that x this holds when x is between 2 pi and 4 pi, and okay, that's just the answer. Alright, it's not even like that hard to just, this is my second derivative after all, right? It's not that hard to just know some things about this function. I'm not sure all of this picture making is even needed, because what is sine x over 2? It's just sine which has been stretched out by a factor of 2, and so it'll have roots at 0, 2 pi, and 4 pi, and it's upside down, so unlike normal sine, it's gonna look like this. And so, if I just kind of know that, then it's just pretty clear that the correct sign chart for this, so I'm making a sign chart now for f double prime, is that it will be negative between 0 and 2 pi and positive between 2 pi and 4 pi, which is the same solution I got here, but I think that was a waste of time. Sorry about that. Okay, what have I just learned? I've learned that this is concave down here and concave up here. And okay, maybe that's not really a surprise because if this is 1 and that's negative 1 and this is 0 and that's 2 pi and that's 4 pi, then as we were kind of just saying, that's what my function looks like. This is the original function now, sine x over 2. And yeah, it's going to be concave down here, and then it's going to be concave up here. So the derivative is decreasing, and then the derivative is increasing. Okay. Sorry to be so slow with that. Okay, 2 more. 27 and 67, and then we'll be done. Oh yeah, this problem. F of x, 27, says f of x equals x minus ln x. Okay, let's go. I want to know, and I should say that I forgot to actually say this, but since the function's concave down and then concave up, then this is a point of inflection. That's what a point of inflection is. It's the point where the concavity changes. Goes from being concave down to concave up. This function's concave down here and concave up here. Okay, second to last problem, I take the derivative, I get 1 minus the derivative of ln x is 1 over x. And, okay, now I take the derivative again What is the derivative of negative 1 over x? Well, it's the derivative of negative x to the negative 1, so in fact the negatives cancel, and you just get x to the negative 2, which is 1 over x squared. Okay, and now this problem is just pretty stupid actually, because 1 over x squared is always positive. And so, yeah, the sign chart for this is just positive always. And thus f is concave up on its entire domain, which is only from 0 to infinity. Okay, good. This was a nice short homework. I used to assign way more problems, but I just decided, you know what, let's just get it done. You guys should really have this homework in on time. Last one is a thinking problem. 67 says, sketch a graph of function having the given characteristics. Oh boy. Okay, so f of 2 equals f of 4 equals 0. Okay, so I got some roots. F of 3 is defined. That's good to know. The derivative is negative if x is less than 3. Oh man. Derivative is negative if x is less than 3. F prime of 3 does not exist for some kind of reason. The derivative of x is positive if x is greater than 3. And the derivative is negative. The second derivative is negative everywhere if x is not 3. Okay. Man, how do we do this? Maybe I'll just do this fast. Okay, what's going on? I don't know, but I'm about to figure it out. First of all, 1, 2, 3, 4. The derivative is 0 here, and the derivative is 0 here. Or sorry, the function is 0 here and 0 here. Okay, so that's done. F of 3 is defined, but f of prime of 3 does not exist. So the function is defined there, but there's no derivative. The derivative is negative to the left of negative 3. To the left of 3. Sorry, that should be a 2. So 2 and 4 at 0. So this function is decreasing up until 3, because the derivative is negative. But it's increasing, the function, after 3. So you would say that there was a relative min at 3. But then also, the second derivative is negative everywhere. Okay, so I think I got this. It's going to be some kind of thing like that. Think some kind of bird situation, and this is 3, and that's 2, and that's 4. I think this works. Let's check. So f of 2 is 0 and f of 4 is 0. Check. F of 3 is defined. Check. The derivative is negative if x is less than 3. So the function is decreasing. Check.